You have a bowl of smooth, melted dark chocolate. Introduce 5 tiny drops of water, and the chocolate survives. But drop in exactly 6, and you cross a mathematical cliff. Food scientists place this failure threshold at roughly 3 to 4% water by weight. That microscopic introduction of moisture triggers an immediate structural collapse. Within 30 seconds, the glossy, flowing pool degrades. It turns into a rigid, grainy mass that looks and acts like wet sand. Standard culinary theory suggests the fat has frozen due to the water's temperature. But scrape the lumps aside and you will see liquid cocoa butter freely pooling around them. The suspension has reorganized into a broken phase. Mastering chocolate requires treating it as a physiochemical system rather than a standard liquid. Melted chocolate is a mechanical suspension. It is dry matter hanging inside warm fat. This cross-section shows the internal architecture. You have 2 primary particulate components: fine, hygroscopic sugar crystals that attract water, and hydrophilic cocoa solids. These solids are suspended in a continuous liquid lipid phase made of cocoa butter. This fat accounts for only 30 to 35% of the total mass, yet it must carry the entire volume of solid powder. This matrix remains fluid because the system is designed around the absence of water. Real chocolate contains less than 1% moisture. Because you have grains that attract water, suspended in a fatty ocean that repels it, this dry equilibrium is volatile. Any external moisture initiates a chemical cascade. Commercial chocolate uses soy or sunflower lecithin to prevent the dry solids from clumping through friction. Lecithin is an amphiphile. Its hydrophilic head attaches to water-loving surfaces, and its lipophilic tail bonds with fat. Inside the suspension, lecithin molecules wrap around sugar grains. Their fat-loving tails wave outward into the continuous lipid phase, acting as lubricants so grains slide smoothly. Without this addition of lecithin, chocolate would require nearly twice as much cocoa butter to maintain the flow rates required for industrial machinery. While lecithin is an effective stabilizer against dry particle friction, it provides no structural defense against liquid water. When liquid water hits the bowl, it breaches the lecithin barrier and makes direct contact with the hygroscopic sugar grains. The reaction is instantaneous. Water acts as a solvent, pulling targeted sugar crystals out to dissolve them. This forms a concentrated syrup. Because cocoa butter is hydrophobic, it repels the syrup, trapping it in a tight bead. This sticky syrup grabs neighboring solid particulates, coating whatever it touches. This is the sugar bowl effect. The syrup pulls dry solids into massive, rock-hard clusters. As these clumps form, they squeeze the continuous lipid phase out of the way, pooling separately from the agglomerated mass. A seized bowl is a broken suspension, a phase separation driven entirely by a rogue pocket of aqueous syrup. This molecular breakdown is often caused by the most common tool in the kitchen, the traditional double boiler. The double boiler has a specific thermodynamic flaw. It relies on simmering water, generating continuous vapor directly underneath a cooler upper bowl. That vapor condenses into liquid. A single drop detaching from the side of the bowl or the lid introduces the moisture needed to trigger a systemic collapse. Microwaving provides a dry environment for heating. Using short intervals with microwave radiation eliminates the presence of steam entirely. Traditional culinary methods often maximize the probability of introducing the exact variable that destroys a lipid suspension. Fixing a seized bowl requires crossing a liquid saturation threshold by adding significantly more water. The ratio is specific. For dark chocolate, you need at least 15 milliliters, 1 tablespoon, of water for every 56 grams of mass. This influx of solvent provides enough volume to fully dissolve every dry sugar crystal in the bowl, breaking the clumps apart and forming a uniform, continuous aqueous syrup phase. Once you have a uniform syrup phase and a uniform liquid phase, mechanical whisking forces the two to lock together. A smooth ganache is a seized suspension that has been forced entirely into a stable oil and water emulsion. These phase mechanics govern tempering, the thermodynamic process of forcing lipid polymorphism. During tempering, you manipulate temperatures to make cocoa butter molecules stack into a highly stable Form 5 crystal array. This crystallization process requires an unbroken, pure, continuous fat phase. Water dismantles this molecular architecture. By destroying the continuous fat phase and agglomerating solids, Moisture eliminates the conditions needed for cocoa butter to align properly. To master chocolate, you must respect the physics of water. You either defend the dry suspension or commit to drowning the system to force an emulsion. There is no middle ground.